All right. Thanks, Albert. It was a great talk. I really enjoyed that. And also thanks everybody for joining. And thanks for the invitation. It's kind of nice. So I don't know if you guys noticed, but I actually was a PhD student in the Netherlands, and I visited the CWI now and then. I was a student of Ilke Visser, who I'm sure you all have very fond memories of. And so it's kind of nice to be back in this group again. Now I am the VP of Engineering at RelationalAI. I will be presenting today, but of course I'm presenting the work of the team, for that's obvious. And there are a bunch of them on the call here as well. So if there are questions, and then they can also help. If you have questions during the talk, that's fine with me. It might be good.
Yeah.
It would be nice to also have a clean recording, of course. So like maybe judge what you want to do. Yeah. Okay. All right. So before I start, I would like to encourage you to watch a different talk first. Because we had a few weeks ago, we did a talk at the CMU database seminar, and I deliberately tried to not do the same talk because that's, yeah, you can just play the recording then, of course. So I'm going to try to cover different topics mostly. And now, at least for the audience that is watching the recording, it will probably be better if you start with the other one first, because that is a more general overview of the entire system. And I'll try to cover some deeper topics today. Yeah. Okay. All right, so let me briefly start by what RelationalAI is. So RelationalAI is a database system for intelligent data apps. Intelligent data apps are built on the modern data stack, and they typically include aspects of machine learning, optimization, predictive and prescriptive analytics. So we think that those kind of applications are best implemented with relational knowledge graphs, which I'm going to talk about today. And as far as I'm aware, there's no database system really designed from the ground up to manage such knowledge graphs at scale. And I'll get into what we mean by knowledge graph exactly and why I'm saying that. Yeah. So before we dive into the details of what RelationalAI system, I want to briefly explain how we see ourselves fitting in the modern data stack. And that is on this slide. So like as mostly probably all of you are aware, in the last 6 to 7 years, there has been a movement towards infrastructure that is cloud native. So cloud data platforms like BigQuery, Snowflake, Databricks, they provide infinite storage capacity essentially because they use the cloud as a storage layer. And they also have essentially infinite compute capacity that they can offer because the compute can scale independently of the storage. Yeah. Now large organizations, big enterprises, they typically have many thousands of applications around. And all of these applications have been architected in an application-centric way, which means that they all have their own database. Yeah. So this is a nightmare for data governance because like these schemas are not integrated and they don't follow the same standards. So the way that the modern data stack tries to address this problem is by bringing the data from all these applications into these cloud data platforms like Snowflake and Databricks and BigQuery. And then you end up with all the data of all these applications in one system. And now you can join across those systems and do useful things with the data. Yeah. And typically that's being used to, let's say, serve BI tools, do feature engineering, and host data apps. Okay. All right. So the cloud data platform vendors, they do not typically claim to support the workloads of, let's say, graph analytics, reasoning, complex business logic, machine learning, and optimization. So these data apps that use that kind of functionality, they require you to go into some other system, often procedural or navigational or tensor-based, like in the machine learning world, to build models and applications. So these systems, they are not cloud native, and they lack the rigor and the scalability of relational databases. So every time you leave this beautiful cloud data platform, you get into an environment that does not have the nice features of the modern data stack, like SQL, versioning, data sharing, infinite storage, and so on. Yeah. So graph database systems like Neo, Neptune, and TigerGraph, they are not originally designed to be cloud native, and they don't scale in these ways. So in general, this applies to any system really. Of course, like basically, if you were designed before the cloud native trend really started picking up, you're typically designed to be an on-premise system. So the value proposition of RelationalAI is that we aim to complete the modern data stack by allowing people to not leave that cloud native environment. So what we try to do is that we acknowledge that current SQL relational systems cannot support those workloads, but we invented new algorithms and techniques that we think makes it possible to support these workloads, like reasoning, graph analytics, and optimization with a relational system. Yeah. So now what you get then is that the modern data stack becomes a larger box that has the original cloud data platform in there, which we sync with, as well as a relational knowledge graph. So we basically try to bring data apps into the modern data stack so that they become relational and declarative instead of the current situation. And I'll explain a little bit more what that exactly means later. Yeah. Okay, so there's roughly 6 topics where we think we're innovating compared to other systems. That is, the first one is immutability, and that is pretty well covered in the CMU talk. So I'm mostly just not going to talk about that. We have an expressive relational language, REL, which I'm going to cover a little bit more today than we have before. We use novel join algorithms. It's the worst case optimal join algorithms that Gabor just mentioned. Those were pretty well covered in the CMU talk, and I'm going to try to not cover those. We do semantic optimization in interesting ways. I'm going to cover that more today. We have a vectorized and a yet compiled system for these worst case optimal joins. And we are a very live and incremental feature, live and incremental system. And we're going to try to cover that today as well. Okay. All right. So before we start with that, I want to show you a little bit the architecture of the overall system. I'm going to show that from 3 different angles: from a language view, from a deployment view, and from a creative processing pipeline view. So first, the deployment overview. So this picture basically shows our cloud native deployment architecture. So databases are persisted in cloud object storage. You see it here at the bottom. It could be S3 or whatever other cloud provider has. Our data structures in there, they're paged, they're write optimized, and they are immutable. And the entire database, including the metadata, is versioned in there as a single version data structure, which gives us serializability. So we use key value store, but we only use that for keeping the root to the database. And we rely on the compare and swap functionality in the key value store to atomically update the database to a new version. So like I said, the CMU talk covers this really well, so I'm going to try to not talk about that further from here. So then we have engines. So those provide the compute capacity. They are entirely transient, so they can go away and the database will still be durable in object storage. They cache data on disk and in RAM. They support larger than memory and larger than disk workloads. And we aim to have 2 offerings. One is a serverless engine where we manage your workload. So we do the workload management entirely for what you submit. But customers can also manually do workload isolation, and then you create engines specifically for your situation. So this is roughly what BigQuery does, and this is what Snowflake does. And we think we can combine those 2. Then on top of there are multi-tenant services to interact with the system. They're based on JSON and Arrow. It's a little bit similar to Aeroflight. And then we have SDKs, of course. And then on top of that, there is a console experience, command line tools, VS Code plugin, and various applications that you can build. Okay. All right. So the interface into the relational AI system, which is intended to be the blue box here, is a very expressive relational core language. May be better understood as an intermediate representation. The overall system builds on the LVM, Julia language, and in some cases specialized solvers. And the REL language itself, which is the box here, is the most general and expressive language in this picture. And we expect that users will use that for the complex business logic, reasoning, machine learning, and graph analytics. However, we recognize that people, of course, have the need for interfaces with other types of languages. And so, for example, of course, people use SQL, and we're working on a SQL interface into the system that is currently in a prototype state working with DuckDB. I got my t-shirt this week. And we think that the algorithms and the data structures of the underlying system can basically support all these languages that we're stacking on top of it. So currently we are working on RHEL, SQL, and Legend. And we have evaluated these other three, like GQL, Sparkle, and GraphQL. And we in principle see no problem with implementing that. It's just a matter of work. Yeah. So for data ingestion, our relational graph model, which I'll get to in a little bit how that works, is suitable for ingesting basically all these formats. The green ones are currently supported. One thing I'm particularly happy with is the JSON support. We have very good support for a high fidelity JSON representation that is also relationally efficient. Okay, this is the query flow picture. So this picture shows how a RHEL model is analyzed, compiled, and evaluated by our engine. The flow is not entirely a standard database diagram. So first of all, it's important that a RHEL model is modular and typically consists of thousands of different definitions. We'll get into a little bit what these look like. And these definitions can possibly be mutually dependent. So you're compiling a very large amount of code typically. So the dependency analysis here creates an acyclic graph of strongly connected components out of the RHEL model. Some other components like type inference, they operate on the strongly connected component graph. The other component that's a little unusual here is the semantic optimizer. We will get into that, what it is, but it performs very significant restructurings of computations using the knowledge of the semantics of the operations that are in the database. Now, one thing that is interesting is that I kind of drew it like a pipeline. This curve is just because otherwise it wouldn't fit. But it's actually not an actual pipeline because the entire system is demand driven. So you ask for the result and then everything happens that is needed for that result. So let's say, for example, you could ask for a view and then everything that's needed for that view will be done. So we use a compiler architecture for that is very similar to how compilers are developed for IDEs these days. That system is called Salsa, and that's sitting here at the bottom, which is essentially a little metadata database that we use for keeping for tracking dependencies and caching compilation results. And if we have enough time, I'll get into that. Okay, so I need to briefly explain what our relational graph models are, because otherwise there might be some misconceptions creeping in that will be confusing. Yeah. So first of all, very simple directed graphs. Like, of course, everybody here probably understands that a directed graph can very easily be represented with a binary relation. Every edge is just a tuple. So 3,1 is a tuple there, and 2,1 is a tuple, for example. Yeah. You already can see this is not a table. It doesn't have headers, let's say. Yeah. It is just a relation, a more mathematical relation maybe, which is just a set of tuples. So labeled property graphs can be represented in that way as well. For example, the properties of nodes are binary relations. Like if you look at the title of the movie, like the movie June, that we report that the title of movie 3 is June. Yeah. The labels of the nodes are unit relations. Like let's say node 1 is an actor, and node number 2 is a director as well as a writer. Yeah. If you have a property on an edge, like an actor acted in a movie, then that becomes a ternary relation. You see that here. The role of the actor 1 in movie 3 is Paul Atreides. Okay. Sorry. Yeah. All right. So next, let's take a look at tables. This is going to look a little different from what you may be used to. For people who are familiar with PGQ, they probably have, you know that, let's say, PGQ provides a graph model on top of a table. We flip that around. To us, a table is a view on a graph. Yeah. So this picture here is showing like if I ask you to draw like basically a diagram on a whiteboard for like this data model, you will probably come up with this. So you have an order key here, an order that has a link to a price and a date and a customer. And there's another order that links to the same date, incidentally, and there's a price and a customer. Yeah. So we basically decompose a table in much smaller relations that resembles a graph very much. And this is basically the same as what you would otherwise see in PGQL. Yeah. So we kind of see SQL tables as kind of as a modularity construct, in the sense that they group relations with the same primary key together. Yeah.
I had a quick question.
Yeah.
So what do you gain if the primary key is just grouping a set of attributes together? What do you gain by this decomposition? It just looks like a table where you could just map one table to one relation and it just has a primary key constraint.
Right. Yeah. Thank you for the question, by the way, because I started to wonder if my audience is still there. So what you gain by that is mostly extensibility and flexibility, right? Let's say like a table is evidently not a graph. And so incorporating that in a graph query requires mapping it into a graph somehow. And let's say in graph schemas, you can much easier add like an edge or a property to an existing node. In SQL schemas, that requires some surgery on the table. Like you would have to later decide, am I going to add a column to it, or am I going to put it in a separate table? And then if maybe your key even changes, you get a lot of, well, lack of flexibility, let's say. So we see this as the more general flexible model on top of which you can layer table views. And I'll give a few examples of that later as well, how we exploit that exactly. Yeah. Okay. It might take some more time to really get that point across. Hopefully, throughout the talk, it will become more evident. Yeah. Okay. So then, yeah. I'm going to continue. All right. So next, tensors. So tensors can also be represented as relations. So if you have a vector, like a vector 418, that can be modeled as a relation. The first argument is the index, and the second argument is the value. And similarly, a matrix is a relation, a ternary relation with two indexes. Yeah. Now, so this highlights to us that the relational model is really very universal, and the challenge is basically that the system needs to understand the information that is provided into the system and implement efficient systems for it. Yeah. So going to a slightly more complicated example, like if we do matrix multiplication, then it's very easy to express a relation actually. So this is the math for it, right? And this is in REL, this is our language. So I'm going to show more of that later. Basically, it's just a textual rendering of this mathematical formula. So the matrix multiplication of A and B, you just combine the indexes in the appropriate way, and that is the matrix multiplication. Here's the SQL variant. I'm not showing this to complain about SQL or something. Like this version is longer, evidently, but there's also definitely queries in SQL that are shorter than RL. Yeah, we are just more suitable for this tensor notation, and so things that are tensor-like typically show well in REL. Okay, and now key is that like this already actually performs fairly well in databases for sparse matrix multiplication. Now for dense matrices, we just need to find the right mapping of these relations into dense data structures. And we see that as the challenge to database systems. So if you go back into the original paper by Cott, then he actually says there is that the goal is to yield maximal independence between programs on the one hand and machine representations and organizations of data on the other. And a little bit philosophical or preachy maybe, but I feel like potentially databases have maybe been lacking some ambition in this area because we always stick to tabular data and B-trees and certain data formats that are all kind of similar to what the logical view looks like. Well, maybe much more aggressive compilation and understanding of the data could be possible to compile into efficient systems. Okay. All right. I'm going to next discuss a little bit the semantic layer, which is a term that has been coined recently.
Martin.
And it's yeah.
Can I stop you just for a minute here? So
yeah, sure.
what you're trying to do, basically, if I understand well, is you want to map everything into a graph, relations and matrices and tensors, and you're going to have an execution engine which operates on the graphs.
Yes.
Is that okay? That's the goal? Okay, excellent.
Yeah. Yeah. Yep. Yeah, that's accurate. Yeah.
Because what most systems did so far, is they tried to basically take graphs and map them as relations because we know a lot about those. So will you get to tell us basically what we gain out of this?
Hopefully it will become clear. Okay. Like there's of course some distinctions in some things that we do slightly different. Like for example, key here, if I go back to the previous slide, is that like this is a ternary relation, like this matrix. Like we are not restricted to binary or ternary edges, so our model is much richer, and so you can basically represent arity relations, for example. And so we think that this relational model that we're going for is the more general universal model that with sufficient effort can implement all the different applications that we're aiming for in terms of graph analytics and machine learning. I'll show you examples of that. Like I'm going to show examples of code in REL that you would probably not think of writing in a conventional relational database system before. Yeah.
Excellent. Thanks.
Hey, Martin.
Yeah.
Hey, I just want to make sure that there isn't a misunderstanding. So our core model is relational, and graphs, hypergraphs, tensors, JSON documents, all tables, etc., all built from that. So it's not that the core model is graph and we map everything to graph. It's a highly normalized relational model that supports all these other views that people want, like graphs and tensors and so on.
Okay.
Okay.
Yeah. Yeah. The reason that I usually, sorry, go ahead. Yeah.
My question was the decomposition of one regular relation and its attributes into the many, many relations essentially also has no implication on the storage itself. So it might be possible that a particular customer will never see that decomposition and will just store it regularly as just a regular table and have their columns or whatever the storage is, right?
Yeah, like we're aiming for maximal independence, right? Like, of course, we currently make certain decisions on how we do store things, but we have maximal flexibility to organize the data in whatever way we want for the specific purpose of future applications. Yeah. Yeah. Okay.
Thanks, Martin.
All right. Okay, so let's go to the semantic layer. So it's going to be a little bit of a sidetrack, but it will be interesting, I think. So people started to realize with these cloud data platforms that it's amazing to have all your data in one database system, but it's actually still very difficult to work across all these systems, of course, right? You're bringing the data into one place, but it's not necessarily integrated in a sensible manner. In various circles, people have started talking about adding a semantic layer to these kind of data systems that let you define concepts and relationships that overarch these data sets. I'll show examples later what that means. So we really like that. We think it's a great idea because the way that the models get richer with this trend is really pushing databases into a place where we think they should be. Yeah. So one prominent player in this area is DBT. They built on top of SQL, and they aim for to be the semantic layer on top of the cloud data platforms. Yeah. Now there's a whole category of those languages that have similar ideas behind them. So there's DBT, there's Power Apps from Microsoft, there's LookML, the original modeling language behind Looker. There's a new language from that team called Malloy that is similar in nature. And from Goldman Sachs, there's Legend that is similar in nature. We like to think of the ambition of REL and our system as something along these lines, and not necessarily as a language that just only answers very small queries, let's say. Like we think that the modern data stack needs to be extended with relational knowledge graphs, and that the relational knowledge graphs are the right answer for the semantic layer problems that people are bringing up. And we're going to explain what those problems are. Yeah. So the example that I really like is this example from a very simple domain that you all probably know. So imagine that you want to develop an intelligent data app for an order database, for example, TPCA. It's considered a very small, old benchmark, not very complicated schema. Yeah. Now we may want to include some analytical features in there for tracking a metric for the average charts of an order. Yeah, so the charts of an order. It's a very simple measure. So this is where the problem actually already starts, because if you would want to show the charts of an order, there's actually nothing in the TPCA schema that is called charts. It doesn't exist. Yeah. Now the term is actually used in the description of some queries. This is kind of funny, but it does not exist in the schema and the data model. Yeah. Now there is in the order table there is actually a column that's called total price, which actually turns out to be the charts that basically aggregates the line item charts and puts that data into that column. It's supposed to be the same number, essentially. Yeah. So this is a pretty common issue that we see, that basically data is computed and materialized and kept into the system. And of course, it leads to all kinds of inconsistency. So this really small example already illustrates that in organizations, like people use different terms and there's uncertainty of what people mean exactly, like is total price the chart? I don't know if that's right. And so if we not clearly define these concepts, then the system cannot answer questions about it. Okay. So let's define these concepts. So this is the definition of charts in REL for line items in order. So for the charts for a line item is the extended price multiplied with the discount and the tax and all that kind of stuff. And then the charts for order is to just sum it up. Yeah. I'm not really going to explain the syntax. Hopefully it's kind of get what it means. The exact syntax doesn't really matter. So this is revenue. It's very similar, of course. You also compute that for extended price and you aggregate it. And then this is an order that is received late. So we define in the semantic layer, in the model, we define out specifically the term received late. And we define that means that the commit date is less than the receipt date. So now let's say in a BI tool or another environment, you can now ask about orders that are received late. Okay. And so, of course, these form a dependency graph. So that is where some of these graphs come from. Like in DBT, you have such a dependency graph as well, in the sense that the things mutually depend on each other. Okay. All right. So to further emphasize the need for this, here's a fragment of a table with flight data that's taken from BigQuery. And the data, frankly, is so unclear that it is very hard to imagine that any BI tool or data governance tool can actually figure out what this means. And this is basically the reason that people are working on these kind of semantic layers. Like at the most basic level, BigQuery does not even indicate that this thing is a primary key. So that we already don't know that. Maybe it is ID2, maybe not. You would have to figure that out. For the flight time, the number is an integer. Now, based on your human understanding, you have to interpret that maybe this means minutes. I don't know, it could be anything really, right? The unit of the distance column is not specified. It could be kilometers, could be miles, I don't know. The delay column is the same story. It's probably minutes. Then also it has negatives. So it's not really delay. It's more like the delta in the departure time, I guess, right? And let's say if a flight is canceled, then the flight time is 0. So now imagine, let's say that you actually go aggregate this data and you want to know on average how long it takes to fly from here to there. You have to consider that there may be canceled flights in there with a flight time of 0, right? So that's going to mess up your aggregations very easily. Now, of course, it's easy to say like, well, this is a really bad data model. They shouldn't have done that. But sadly, in practice, this is how people apparently model their data often. Yeah. Okay. So it would be much better to have a better precise model that really conceptually documents things very clearly. Like, for example, a flight has a flight time, which is a minute. A flight can be either diverted or canceled or arrived, but not all 3 of them. This means that these are mutually exclusive. We also indicate primary keys and functional dependencies in this model. I want to show you what it looked like in REL. So in REL, this can be written as follows. Like, again, I'm hoping that the syntax is intuitively clear. Like we clearly define what flights are canceled, diverted, and arrived. Where they say there's a set of canceled flights, which is a flight, and a flight is canceled is it have that string on its field. Yeah, it has arrived if it is not canceled or diverted. We also define arrival delay as the actual delay, so the maximum of the minute 0 and the arrival delay that we found in the database. And then on top of that, we can start writing integrity constraints that document what the expectations on the data are. So let's say every flight has to be either canceled or diverted or arrived, but not 2 of those. Yeah. And also if a flight is canceled, there cannot exist a flight time. Okay. So now with the clarity that we added to this model, you can now much easier query the system. So let's say you can count for canceled flights. You can count for canceled flights grouped by the operator, the carrier. You can ask for the ratio of the canceled flights by destination airport. You can ask for the mean arrival delay, and you can ask for the mean arrival delay by carrier, let's say. Yeah. And of course, if you know the data model really well, you can write these queries correctly as well against the original schema. But here we're helping you write these things correctly by having the right concepts in your model. Okay. And you can probably already kind of get a sense of this, is that like I'm kind of adding all kinds of bits of information here. If you would have to do this in a SQL environment, then you would have to decide, oh, in which table I'm going to put this. I'm going to put them together. I'm going to put them separately. Do I have too many tables? And here you just define information bit by bit, very similar to how you would do that in a labeled property graph. Okay. All right. So we think this is really important to actually start documenting these conceptual models very clearly inside of the database. So the semantic layer and reasoning, from our perspective, subsumes and captures the app logic that is currently still written in procedural languages. So we have conditioned ourselves to build our applications in the split brain architecture. And part of the application is in SQL, part of your application is on the client. And what the application is trying to do is not coherent at any point, basically. So we cannot optimize across those layers. And we think it's really about time that we start expressing these kind of things in the database itself. And it makes it possible then for the system to entirely manage the entire integrity of the application. So we've been working on this for a while, actually, on this kind of applications. And we typically see that for the applications that we start attacking, that we see like a factor to 10 to 100 times reduction in size of code, just by declaratively specifying in one coherent place all the business logic. All right, okay, so I've already shown you bits and pieces of the REL language. I want to show you a little bit more of the overall motivation of where we're going, so that it's really clear what we're doing here. There's a list of design objectives. I don't really want running quite late, so I don't want to go into too much detail. Key is here that we aim for abstraction. So it needs to be able to develop libraries of reusable components for example, statistics and all kind of stuff. That needs to be cheap. So these libraries cannot have a cost. And we want to also write these things as generically as possible so that you can abstract over schemas. You need to be able to write generic functionality that can be instantiated with a specific application. And everything is supposed to be live. So you need to be able to change it, support schema changes, and be able to gradually refine your data model. So I'm just going to show a few simple examples first of what that means. Is that in REL, you can define statistics very easily. This is in the standard library, so you just use them from the standard library. They're defined in REL, and the system is not aware of it, and it just compiles it in whatever way the system capability does that. So, for example, mean is just defined by the sum divided by the count. Frequency is the count of the individual elements. The MSE, which is a typical machine learning cost function, is the sum of the difference in the prediction divided by the count, and the RMSE is the square root of that. Now, this might look a little bit complicated maybe, but really it is just a rendering of the mathematical formula, and we're just writing that thing down, basically. Yeah. This example is the graph analytics library. So this is a module that you parameterize with the graph that you want to use it with. So you give it the graph, and then you get all these algorithms that you can work with. These are mostly fairly straightforward, but you get things like out degree, in degree, reachability, strongly connected components, weakly connected components, and similarity metrics. Now, if you look at these and you read them very quickly, then you might think, oh, these are very naive. This will not possibly work. So we're going to get into that because we have methods in our semantic optimizer that optimizes these algorithms without you having to very specifically write them in the most optimal way. And that is very important for us to support these kind of abstractions. Okay. All right. One example that I want to give briefly to sketch out where we're going with this schema abstraction. If you look at a typical feature engineering workflow of a data scientist, then they often use this function called describe. It's a very interesting function. So they have a data frame. A data frame is kind of like a set of relations, right? And they give it to the scribe, and the scribe function reflects over what is in the data frame, and it shows you a bunch of statistics about the data in there. So like maybe for numeric things, it might give you averages, but for things that are not numeric, it might give you the most common value and all kind of stuff. Now, in a SQL system, you can't write this in SQL. You can't reflect over a table easily enough without a code generator, at least. In SQL, reflect over a table and provide this information, let's say. So in REL, you can do that. So we have generic programming features in place where you can generically use the feature set that's being passed in, reflect over what the types involved are, and generate the aggregates that that you want to see. So this command here is really a command that works in Rel. So you give it the feature set, and then you get this table back that describes the data. To further expand on the machine learning capabilities, like these are some abstractions for feature scaling. So typically, if you do machine learning, you need to scale your features for the model to work well. And so things like min-max normalization and z-score normalization, they're defined within the Rel language, and you just use them as a library in your logic, and the system compiles them efficiently. Similarly, here's a linear prediction function. Again, that abstracts over schema, because like a feature set is actually a collection of relations, which is essentially is a schema, and you can generically over that schema ask for a linear prediction function with the feature set that you pass to. Now, this is very quick, of course, and this is probably not 100% clear, but actually explaining how that all internally works is quite a bit more work, and I can't really cover that today. So, yeah. And then this is sort of the ultimate where we're going to is we have an additive feature, which is called Jacobian here. So you can take the gradient of a cost function, and then you can write a recursive loop that does the gradient descent training. Very similar to how that works in TensorFlow or other frameworks. You instantiate it with your feature set with these normalizations and scaling in there, and your response, and you get a model back, and you can use that to answer to do predictions. Now, this of course will build on a whole stack of efficient machine learning algorithms, acceleration optimizations. But this is basically the ambition that we have, is that we want to define complex mathematical models in Rel beyond what you would probably normally define in a query language. Okay. All right, so I'm really going way too slow, so I'm going to skip over some sections. As I mentioned before, we're doing a DuckDB interface. We love DuckDB. I saw some people in the room already from DuckDB. We have a collaboration ongoing where DuckDB is the SQL interface into our system, and we have a prototype working of I think the TPCS queries at this point all validate, we're very excited about the collaboration. It's going well. It's a very solid product that we're very happy with. So yeah, I'm going to skip the next. So semantic optimization is probably the most interesting part. So yeah.
Martin, very, very quick. How do you deal with user-defined functions? Can I include them in Rel? How does this work?
That's a good question. We would have to see, like, let's say of course the existing SQL functionality. Actually, no, this is easier. So currently the way with we integrate with DuckDB is that we give them access to our data structures. So whatever user-defined functions DuckDB would support, we would just evaluate as is basically. We do want to pull that up the stack because DuckDB in this way does not inherit all our system properties, and then eventually we would take over some user-defined functions potentially. Yeah.
Okay, so you would push them down to Rel as
yes. Yeah.
Okay, thank you.
Okay, all right. So semantic optimization. The idea here is that at a very high level, this is that there is a Rel model. We have some knowledge. I'll get into what it is. We have a semantic optimizer. We have data, and we want to optimize this Rel model into an optimized Rel model that gives you an answer faster. Okay, and the knowledge basically describes a set of equivalent Rel models, and the purpose is to find a good one in that space. Okay. Now, what is the knowledge exactly? So first of all, those could be user-specified constraints. So this could be things like functional dependencies, total functions, disjointness, and so on. They're very often mathematical axioms, and like things like semi-rings and rings and all that. I listed here a few, like let's say, distributivity is very often exploited of various operators. Yeah, and then also some of these knowledge is learned from the data. So of course, summary statistics, histograms, and cardinality estimation. To give you a quick impression, I'll give you a very simple example. Like let's say that you take a minimum of fi plus gj. So you're taking the minimum of this addition. Now these are independent, right? They have no common variable I and j. So that means that you can actually push down the minimum into the arguments and add them up, like the minimum of f and the minimum of g is the right answer. Yeah. So that is the kind of analysis that we do in our system. Now, if you make them dependent, then that is not valid, of course. You can't take the minimum of f and the minimum of g and then add them up, because they might be minimum for different indexes. That doesn't work. It's not correct. Yeah. And then similarly, an example that does work, if you do a count of a Cartesian product, then the optimizer can conclude that you can separately count f and g and multiply the answer. Okay. This is to give you a flavor of what this kind of optimization is about. And surprisingly, many current SQL systems still don't do that. Like in particular, even this Cartesian, I keep saying this, at some point I'm going to regret this, but like even these Cartesian products, they often don't do yet actually. So now, so this is not ad hoc. It's very important to understand. Like we have deep understanding of semantic understanding of the logic that's being compiled. And so this is not syntactic or based on pattern matching or something like that. Like for example, if I do a count of R, S, and T, but I add a condition to it that makes these things somewhat dependent, then that actually is still compiled into a correct decomposition where you consider B less than C and A less than B and still have an optimization that optimizes it as far as it can do, considering the dependencies that do exist between these variables. Yeah. Another example is, it's kind of cool, is that let's say if you count R and S and you ask X and Y to not be equal. So that is a dependency, of course. So you can't independently count R and S now. So we actually utilize the knowledge that that is the same as the count of the cases where they are equal, let's say. You can invert it and then do the subtraction, basically. So that's exactly what we do. So we count R, we count S, and then we count the cases where they're equal, and then we subtract that from the original result, and this is faster. Yeah. This is an example from the LSQB benchmark. This is a count query, and this is the visualization as you show that. So a person knows another person who's interested in this tag, and they, oh, sorry, this arrow is wrong, it should be here. And these two cannot be equal, yeah? So now this is pretty tricky to optimize. I actually have difficulty explaining the optimized result, frankly. You really can't come up with this. But this uses the optimization from the previous slides to basically turn the inequality into an equality, and then compute first an overestimation of the count, and then subtract the error that you introduced while doing that. Yeah. Now, what you see is that like we really respect Umbra, and I don't really want to say anything bad about it. The point is basically is that like if semantic optimization kicks in, we are very hard to beat because this is often such a good optimization that we even on one core are doing very well compared to Umbra on one core and Umbra on 48 cores. Yeah. So this is a very effective technique that works very well, in particular for many graph queries. Now this is another example for a running total. So let's say you probably have seen that in SQL as well. Like a naive way to do a running total is to sum up all the previous values. This is not good because it is quadratic, right? You keep summing up all the previous data. Now, our optimizer, given knowledge about the ordering of the temporal dimension, can actually turn that into a window function, essentially. So to us, these are just recursive computations. So we compute for the first element in the series, it is the initial value. And then after that, you just keep summing up the previous value. So this is our form of a window function. This inefficiency can automatically be compiled into this, assuming that we have knowledge about the ordering of the temporal domain that we're dealing with. Yeah. And that knowledge can then be declared with these things that are also in our library. Like you can specify that something is transitive in partial order and so on. Okay. One of the things I really struggle with in SQL is remembering the window function syntax. So I think if only the only thing we achieve is that you don't have to remember that anymore, that would be great. All right, so then to go further into a shorter path example, like let's say that our library defines a path function that computes the length of every possible path. Now, of course, that there are many paths, and that's not a good idea. That's probably not going to work. And let's say that you then define shortest path as the minimum of the paths that exist in this graph. So you're first computing all the paths, and then you're taking the smallest. Now, so our optimizer actually knows the algebraic properties of min distribution over plus, like I showed earlier, and it can actually push the min into the aggregation and actually do this min aggregation while the shortest path is executing. And then you essentially get the Dijkstra's algorithm. This is of course great anyway, but also like this is kind of key to our library working effectively, right? I will show some examples of it later. This allows us to have abstractions in our libraries that are optimized away depending on how people use them. And then we'll have a further optimization of this is demand transformation. This is still in the development, but we have a prototype working. Is that like if you want to compute somebody's bacon number, then you're going to ask for a single source shortest path, right? So like the distance from everybody to Kevin Bacon, and we can even put the amount of Kevin Bacon in there, and then compute only the specific, only the shortest path from Kevin Bacon. Some examples of these abstractions, like let's say this example that I just gave, is that there's no need in our system for a separate definition of single source versus all pairs. We can reduce the generic path definition and build this optimized into whatever form is needed. The same for SECs, like SECs can be expressed like this. This is not a great definition because the reachability relation is potentially very large, but it will just push the min into the reachability. The same for weakly connected components. And even this one, the mean that I showed before, like this is not a great definition if you would execute this literally, because it would be scanning the data twice. But we optimize that away, and over the entire program, we consider all aggregations, and we just organize them in a way that they're executed efficiently. Okay. All right, I'll briefly go over this. This is the last major section. We aim to support the processing for changes in code as well as data. So you need to be able to change the program as well as the data, and the system should respond incrementally to whatever is happening. So one thing that we do is dependency tracking for everything that's being compiled and processed in the system. So let's say if you compile a definition, then it knows exactly what definition it depends on. And if you change one of these definitions, then the other definitions may be recompiled. Our execution is demand driven, so that if you install thousands of views, that doesn't impact performance. You only evaluate what's being asked for. We use differential data flow to incrementally maintain recursion, including general recursion, including aggregation and negation. We can use, there's a paper in POTS this year, semantic information to determine whether a recursive computation is properly monotonic or whether it may not terminate. And then we use semantic optimization to actually optimize the result of these incremental maintenance algorithms. Yeah. Now this is really important to us because so this is a dependency graph for one of our customers. This is not a graph of the data, it's of the code. So every node here is a view, let's say, a definition. This has over, I think 3,000 relations in there and 13,000 edges between them. And this is not abnormal. This is basically what we aim for. Now, of course, users do not have to understand this. This is very complicated, right? But it's an illustration of the complexity of the code that we're compiling in our system. So zooming in a bit, this is one strongly connected component. These are all recursive, mutually recursive definitions. This is from application and text analysis. We support that, and based on our foundation in a data log and differential data flow. And then this is one node, so you can see how many edges this has. So dependency analysis is quite tricky. It can be very expensive to keep this kind of provenance. So we're spending a lot of time fine-tuning that area. So I'm almost out of time. I want to respect the time, so I'll go a little bit quick over the remaining. I think some people here are probably familiar with differential data flow. It's an algorithm that's also being used by Materialize. So differential data flow is good because it can consider in recursive computations, it considers the deltas from the input changes as well as the iterative changes, and it uses those both to maintain the computations, and that is a very effective method. And this is very important. So in plain data log, which we are based on to some degree, There is no aggregation and negation in recursion. That's just a no-no. That's not acceptable because in graph applications, there are aggregations and negation in recursion. And so to be able to express these algorithms, we do need to support that in our system. And then I wanted to briefly explain the complexities of these demand-driven problems. Is that like we basically have this big dependency management problem for all these definitions. And if something gets changed, then we need to appropriately update the entire system accordingly. So that in itself is already an interesting problem, actually. And so we've been studying that quite a bit. And there's sort of a few different methods that you can use. Like basically eager maintenance of everything is a really bad idea. Your performance will go down the drain very, very quickly. Lazy maintenance is also kind of problematic because every time you ask for it, you need to check if it's still up to date. So you get very expensive checking if your view is no longer correct. And so what we do is eager invalidation and lazy evaluation. So we eagerly mark things as this is all wrong, this is no longer correct, but then we lazily evaluate it once it comes in, and that gives us good performance in this dependency management system. Okay, so I do have a machine learning section, but I assume we want to stick to the time, and I already have been talking for 55 minutes. So I'll give you a quick idea and then I'll move on. So in machine learning, current practice is that you have a relational schema, you put that in a matrix. The matrix is essentially an extremely denormalized table with a lot of redundancy in there. And then the machine learning tools start working over that. So our machine learning algorithms, the way that it works, they actually exploit the structure in the original relational schema. So we don't make the design matrix, we can make it virtually, let's say, but we actually exploit the structure that exists and optimize things so that we don't do aggregations over large data sets that are not actually necessary. So that gives us very good performance results, in particular for problems that have a lot of structure in it. Okay, but I'll skip this. All right, so to briefly recap, I didn't even show everything that we do, but like I highlighted what in green what I talked about today. So RelationalAI does large-scale reasoning. Hopefully that's become clear. Our system is immutable. It's a completely versioned, right-optimized data structure. We do worst-case join algorithms, which are in the CMU talk if you want to learn more about how we use that. Semantic optimization I've discussed in some detail. Incremental computation, the REL language. We do relational machine learning. So our machine learning does not farm out, so let's say, to TensorFlow or PyTorch or whatever. It's actually executed as part of the database system itself. What I didn't cover today is that we also have solver integration. So let's say you can express mathematical optimization problems, and those problems will be solved by like something like Arobi or Cplex or something like that. And so this really gives you the complete set of tools that you often need in these intelligent data apps. Yeah. And then, a little bit about where we are. So we recently closed our Series B with Tiger Global and others. There is a news announcement on that. Bob Murglia, former Snowflake CEO, is now aboard. We're now 140 people with a lot of background. It's really work with all these people, so much experience in there. And we also have a really nice research network that we closely collaborate with. Some people here are on that research network. And we really enjoy working with all of them. And also if somebody here is interested in working with us in any way, then please just reach out and then we can talk about that. All right, that was it.